the origins of structural biology began with Don's involvement in the field. He's been in all the right places at all the right times, and he's been doing historical research and gathering images and stories from the beginning of structural biology, and he's going to enlighten us today on the origins of structural biology. Don.
So I trace the origins of structural biology back to 1927 when J.D. Bernal and W.T. Asprey were about to leave W.H. Bragg's lab at the Royal Institution. That's William Henry Bragg, the father. That they had a gentleman's agreement that Asprey would do the fibrous proteins and Bernal would do the crystalline ones. Now, there isn't anything, any documents to mark this occasion, unlike some other notable events in 1927. There was my birthday in January, and Lindbergh flew across the Atlantic in May, and in October there was the Solvay conference that marked the birth of the new quantum mechanics. Now, Einstein didn't like it, that he didn't like the uncertainties and all the probabilities. He said God doesn't play dice, and Niels Bohr replied, Einstein, stop telling God what to do. But Linus Pauling liked the new quantum mechanics. In fact, for the 2 previous years, he'd been mostly in Munich and traveling around in Zurich and Göttingen and Copenhagen, finding out what what all the pioneers were doing, Schrödinger and Pauli and Heisenberg and Dirac. But when this conference was going on, he was back at Caltech as professor of theoretical chemistry, assistant professor of theoretical chemistry and mathematical physics. On the way back, he had stopped in Great Britain to visit the Braggs, and Lawrence Bragg, this is the son, he was focusing his efforts at this time on the structure of the silicates, which was a complicated and really rather confusing problem. And he was using the science that he had invented back in 1912. This picture was taken in 1913. This was after he had solved the first crystal structures. There's a lot of history in this photograph, but it's, let's see, I better try to keep to the point of my story. In any case, just 10 years after this picture was taken, Linus Pauling solved his first crystal structure while he was starting graduate student at Caltech, and he was in fact the same age that Bragg was when he invented X-ray crystallography, but Pauling obviously had a lot to catch up to compete with Bragg, and that is in fact part of the story. As I said, Bragg at this time, 1927, was concentrating on the perplexing structure of the silicates, and perhaps when when Pauling stopped in Great Britain, that his interest in the silicates might have been tweaked a bit. In any case, he went to work on the problem, and 1928 he published his coordination theory of the structure of complex ionic crystals, which made sense of all the confusing complexity that Bragg was dealing with. So it was, let's say, it was rather serious embarrassment for Bragg. When he published his atomic structure of minerals, this was the Baker Lectures at Cornell University in 1947, that he acknowledged that Pauling's electrostatic valence rule was, in fact, the key principle governing the chemical structure of minerals. This is 1938, back in Leeds. Asprey was summarizing his work for the past decade since he left the Royal Institution, and introduced it with a limerick by Lindo Patterson, amino acid and chains are the cause of the X-ray explains of the stretching of wool and its strength when you pull, and show why it shrinks when it rains. And Asprey, I must say, had very enthusiastic attitude toward the science he was doing. Scientific thrills were among the best and highest kind of thrills, and greatest scientific venture of his time was the problem of structure of proteins. Now, Bragg, that's William Henry Bragg, had set him to photograph human hair for a lecture that Bragg was giving, and this sort of pointed the direction of Bragg's, of Asprey's future career. This is typical alpha keratin diffraction pattern, and this was this pattern was actually recorded in 1958, 30 years after Asprey had left the Royal Institution, but it was the pattern that gave him really the greatest satisfaction in his scientific career, because it was a photograph of a lock of Mozart's hair. And next to X-ray fiber diffraction, I think the thing that Asprey was most enthusiastic about was Mozart's music. But there are two diagnostic features for the alpha-keratin pattern, the 10-angstrom equatorial and the 5.15 meridional. And he showed that you could stretch the alpha-keratins, and then they would change into beta pattern with 4.7 meridional. And the beta pattern, it was obvious that the polypeptide chain was essentially fully extended, but the 5.15 meridional showed that in alpha-keratin, which included great variety of fibrous proteins, including all the muscle proteins, myosin, tropomyosin, and so on, that somehow the polypeptide chain had to be folded. And this was great puzzle, and I think, as you know, the puzzle was finally resolved in the 1950s. But Bragg made unfortunate mistake of concluding from Asprey's pattern that there had to be an integral number of units in this repeat distance. Well, that story comes a bit later, but while Asprey was having a thrilling time in Leeds, Bernal in Cambridge was opening new frontiers as a scientific, it is a very colorful scientific, political and sexual revolutionary at the time, but I think I'll confine my remarks to his revolutionary science, that he was regarded as the brightest intellect in Great Britain at the time. His friends called him Sage because he knew everything. This photograph was taken in 1933 by a couple of pioneering photographers in Cambridge, Lettice Ramsey and Helen Muspratt, and they photographing all the notable left-wing intellectuals in Cambridge at the time. But in 1933, Bernal had just formulated his seminal theory with Fowler on the structure of water and ionic solutions. The year after this picture was taken, he invented Xray crystallography. He found that keeping the crystals wet, he could preserve the structure. And together with his student, Dorothy later Hodgkin, they began to systematically collect crystal data. And Bernal, of course, was anticipating what this would lead to, potentially atomic structure of proteins. That 1936, he was joined by Van Kuken, one of his devoted disciples, and Max Perutz, and also 1936 he started his studies with Van on liquid crystalline properties of TMV. Fan managed to get some beautiful diffraction patterns from oriented liquid crystal specimens. This one, which was probably the best oriented, the backstop had fallen off, but it was evident to Bernal that there was crystal-like order in this virus particle, but with all his intellect in, well, this would have been 1937, 1938, he couldn't see the helical symmetry. This had to wait for the helical year in 1951. So here he is with Irving Langer demonstrating liquid crystalline properties of TNV while DorothyHodgkin was on admiringly. That Langmuir was, this is 1938, that he was quite enthusiastic about Dorothy Rinch's very novel work on structure of proteins. She'd come up with this cycle model that was really mathematically, geometrically quite elegant, and seemed to explain a lot of numerology about proteins, but that probably most people here don't know anything about it. It was very fashionable for a time. Considering Rinch's structure, that Langmuir realized that there was a rather fundamental question: what was driving the folding up of the polypeptide chain to form globular proteins, and he explained it in terms of the hydrophobic effect that removing nonpolar groups from water would lead to significant decrease in free energy. This was in contrast to Pauling's idea that it was hydrogen bonds that were driving protein folding. But in any case, Pauling was very, very sarcastic about Rinch's cycles, and because she was also very sarcastic about his ideas. But Pauling did carry his criticism beyond the scientific level, that he informed the Rockefeller Foundation that Rinch's research was dishonest, and that led to her financial support being terminated. But this is 1939, and marking really sort of end of era, because Bernal was soon off to the war, advising Lord Mountbatten on how to win the war, and DorothyHodgkin turned her attention to penicillin structure, and Fan and his wife were back in the United States. So jumping ahead to 1947, this is Fan's class of what he called his 2-week wonders from his Xray summer clinic, 1947. It was my introduction to Xray crystallography, and I must say I didn't see much future for myself in the field, but particularly since one of my classmates was a distinguished professor from Harvard, John Edsel, and Edsel recognized that that crystallography was the way to understand protein structure, and at the time he was involved in arranging for Barbara Lowe, who was working in Pauling's lab at Caltech at the time, for her to come to Harvard and work on heavy atom derivatives, proteins that he and his colleagues were preparing. He had the right idea that heavy atom derivatives were the way to phase Xray diffraction data, but serum albumin, unfortunately, was the wrong protein because it constantly changed. Well, 1948, the next year, as Barbara Lowe was leaving Caltech, that Herman Branson, a young physicist from Howard University, was on his way there to spend sabbatical with Linus Pauling. And Pauling gave him a task to figure out how to fold up polypeptide chain to form reasonable hydrogen bonds. And Branson came up with two models, one with 3.7 residues per turn and the other with 5.1 residues per turn. When Branson remembered when Pauling saw these models, he said they're too tight. So he said, go back and try to find some looser packing arrangement. But when Corey saw the models that he remarked, I'll be damned, and so spring of 1949, Branson wrote up his results and went back to Howard University, and then nothing much happened for a while. But back in Great Britain, Bragg decided that it was time to try to explore all the possibilities for folding up polypeptide chain to account for Asprey's alpha keratin diffraction pattern. And he made the unfortunate mistake of concluding that because this 5.15 reflection was meridional, that there had to be an integral number of units in the repeat. So all the models they made were integral screw axes, and they were all really pretty miserable models. But this one, the model with the fourfold screw, it has the topology of Branson's 3.7 residue per turn helix, but instead of Branson's rotation angle of about 100 degrees, it was 90 degrees, and instead of uniaxial translation of 1.5 angstroms, it's 1.4 angstroms. But in any case, when Pauling saw this miserable and rather monumental effort from Bragg, he must have gloated it was obviously time to publish Branson's results. On October 6th, 1950, this was then about a year and a half after Branson had left Caltech. He wrote to Branson, including a draft of a manuscript that he proposed to publish in the PNAS, and he said Dr. Weinbaum, who was doing computational work for Pauling, did a great amount of work based on your original notes, and I think that the discussion of configuration for the spirals is in good shape. At the time, Pauling called these things spirals, not helices. And I must say, this is the only evidence that I've been able to find that Pauling actually acknowledged that Branson had done anything. That a week later, October 13th, Pauling sent off a short paper to JACS, authored by himself and Corey, that gave a brief description of the 3.7 and 5.1 residue helices, and that paper ended with generous acknowledgement of assistance from Drs. Branson and Weinbaum. And also, that this was October 19th paper, appeared in November 1950, but so somehow the PNAS manuscript didn't get to the PNAS until February 28th, 1951. That was Pauling's 50th birthday, and the spirals had been changed into helices, or helixes in some cases. Pauling did a masterful job of publicizing well, particularly the 3.7 residue helix that announcing that it explained Asprey's alpha diagram, which it didn't, and structure of hemoglobin and other proteins, but looking at the structure, Max Perutz remarked, years later that as soon as he looked at saw the PNAS paper, this was in early 1951. It looked dead right, it's interesting in his recollections, which were published in 1998. He referred to the Pauling Corey paper, and he managed to forget about Branson. But in any case, he recognized that none of the helical models that had been proposed could account for Asprey's alpha keratin pattern, because that's just the very nature of the helix. The first meridional reflection would be for the unit residue translation, but with all the helical models that have been proposed, the only one with a 1.5 angstrom translation was Branson's. Well, that he thought it was Pauling and Corys 3.7 residue return helix. So he set out to test Pauling's theory by, Chris, with fiber diffraction, most people just hold a fiber perpendicular to the X-ray beam. And Proutz recognized that, if you wanted to see something out of 1.5 X-ray spacing, you need to tilt the specimen. So he tilted a horsehair and a fried muscle fiber and synthetic polypeptide fiber, and sure enough, oops, now, what have I done now? There, okay. There was 1.5 angstrom reflection. So this was June of 1951, and he wrote to, now there I got it. He wrote to Pauling with great satisfaction, and he proved the 3.7 residue helix, and Pauling politely thanked him for his the information, pleased that you should have found the 1.5 angstrom spacing. And then Pauling said, of course, in one of our papers, we had mentioned that this was observed by MacArthur, that was back in 1943. I've not been able to find out when the 3.7 residue helix actually turned into Pauling's alpha helix, but 1952, the papers in certainly in late 52 do refer to it as alpha helix. But there were still problems to deal with. That Bragg had given Francis Crick and Bill Cochran a paper by Vladimir Van that was supposed to be calculation of a diffraction pattern from a helix, and the paper was rather flawed, but Crick and Cochran both got it right, and they went on to show that the X-ray fiber pattern from the synthetic polypeptides, things like polybenzyl glutamate that forms stable, isolated alpha helix, that they were in fact accounted for by Pauling's, I guess we should say Bransons, 3-point residue return helix. Now, Jim Watson had come to Cambridge with the goal of finding the structure of DNA, and Francis was teaching him helix and diffraction theory, and he went off to London to attend a seminar that Rosalind Franklin was giving, and thought he understood what she was talking about, and came back, and he and Francis built a model for the structure of DNA, which had 3 chains and had bases pointing out, and the phosphates in the middle. And they had the King's College people come so they could show it off, and Rosalind Franklin looked at it and said, "You got it wrong. The phosphates are on the outside." But she had clear experimental evidence from her fiber diffraction, and Bragg, Lawrence Bragg, was rather annoyed by this, and he told Crick and Watson to stop fooling around, poaching on other people's experimental work. It was not gentlemanly to try to preempt interpretation of data that was being collected in another MRC laboratory. Francis Crick decided that he would go back and try to make sense of Asprey's alpha keratin pattern, and Jim Watson decided that he would look at TMV, so Francis showed him how to see the evidence for the helical symmetry in X-ray patterns that Franklin had gotten with Bernal. And I must say, Francis Crick is certainly a recognized genius, and when it came to structural work, what he did with the coil, well, that's the answer, with interpretation of Asprey's diffraction pattern is perhaps the most brilliant example of his genius when it came to dealing with structural problems. He recognized that what is called alpha helix, and the alpha helices would tend to pack at an angle to each other, and then they would then naturally twist around each other. Pauling visited the Cambridge lab in summer of 1952, and Francis told him about his ideas about cold packing. Actually, Pauling didn't remember this. He just remembered that Crick asked him had he thought about cold packing. He said he'd answered yes. In any case, Francis published a brief, or wrote a brief note to Nature, the end of 1952, is alpha keratin called coil, and Pauling had submitted a rather lengthy paper on cables of alpha helices. Actually, Pauling's very long paper had arrived just shortly before Francis's, but Francis's paper got published in December, and Pauling's didn't appear until January. In let's say 1953, this was March 1953, 14th of March 1953. Francis Crick submitted two papers on called one, which was a heroic calculation of the Fourier transform called coil, and then his analysis of the packing, and that he ended up calculating the diffraction pattern from coil, starting with just Asprey's 5.15 meridian reflection and the alpha helix. This paper, let's see, it was submitted 14th of March 1953, and 2nd of April, 19 days later, this bombshell paper by Crick and Watson on the structure of DNA appeared in Nature. And of course, I'm sure probably everybody knows nowadays that the solution to the double helix was Rosalind Franklin's photograph 51. But with the coil, there was no photograph 51. Francis Crick had calculated his own photograph 51, and it took another 8 years before that pattern actually saw the light of day. But DNA, that the history of how Watson and Crick came to solve the structure of the DNA, this intimately involved then Sir Lawrence Bragg and Linus Pauling. That Pauling wrote, let's say, it's probably one of the worst papers that any scientist has written. His model for the structure of DNA that had appeared in Cambridge in January of 1953. He ended up making a model for the structure of the deoxyribonucleic acid, the acid that could only exist in strong acid solution. He had hydrogen bonds between the protonated phosphate groups, and that you know, if I can imagine if one of his students had done something like that, scathing response they would have gotten. Oh, and also it had 3 chains, like the abysmal model that Watson and Crick had come up with in December 1951. So Jim Watson brought Linus's paper to Bragg and said that you know, if we don't hurry up, Pauling is going to beat us. You know, you have to terminate the moratorium placed on our model building. That you know, that there was a race with Linus Pauling, but actually the race that Watson and Crick had was with Rosalind Franklin. But, you know, they had to race to manage to publish their interpretation of her photograph 51 before she did. And you know, Max Broods helped out by passing on a medical council, medical research council report he had, in which there was some of her hard data. So that you know, Jim maintained that you know, Rosalind couldn't interpret her own data, but you know, she could see the helix cross count, the ley lines, saw the acids of the fourth ley line, that meant that the 2 chains were not equally spaced. Measuring the position of the inner maxima, she could calculate the radius of the double helix. So, you know, 3.4 angstrom between base pairs, 34 angstrom pitch, 10 base pairs in that distance, radius 10 angstroms, the chains 3/8 of the repeat period separation on the narrow groove. And of course, another important feature is the anti-parallel backgrounds. But when she wrote her draft manuscript in 1953, before she had seen the Watson and Crick model, that she had not noted this, although the evidence was clear from her analysis of the crystal in A form. In fact, her notes on the Patterson function, she had included this. So writing the paper, the problem was how to obscure the fact that where the data had come from. And you know, they said here that, you know, that their structure rests mainly, though not entirely, on published experimental data and stereochemical arguments. Well, not entirely was photograph 51, which was you know, almost the whole story. But having Rosalind's backbone, then it was pretty straightforward to build in char gas base pairs. And you know, Jim had found that the only way to make suitable hydrogen bonds was to have the two bases upside down relative to each other. So then Francis said, well, you know, they have to have a perpendicular twofold axis, and you know, Rosalind's data showed that it was a perpendicular twofold axis. Well, in any case, this was, I think, really a stroke of genius in writing the paper. Rather spectacular understatement about what had not escaped their notice. With that, how was anybody going to ask them, you know, where did you actually get the data? When September 1953, you know, all the characters in this story were together at Caltech for a meeting that Pauling had organized to celebrate the alpha helix, and you know, there he is with Corey, that Max Perutz had you know, just succeeded with isomorphous replacement method, which meant you know, protein structures could finally be solved. There's Jim Watson and Francis Crick. Asprey, who with Bernal had started to go off. Bernal was not there because he couldn't get a passport. He'd gone to a peace meeting in Moscow, and DorothyHodgkin was not there because she decided to go with Bernal. There's Edsel, who I told you about earlier, and Barbara Lowe was working with him on crystallography. You know, Max had the right protein for the heavy-handed derivatives. Center of the photograph is Lawrence Bragg. You know, buttons don't like to work. So this is Rosalind Franklin. I think you noticed she was not at that Pasadena meeting. And she was not there because she was not invited. This was SIBA meeting in London, 1953, where she described the correct symmetry for tobacco virus particle that Jim Watson and Francis Crick had recognized the helical symmetry, but he tried to count how many cellulose per turn and got the number wrong. And well, Rosalind did it together with her student Ken Holmes, and she also at the same time had established the location of the nucleic acid buried between the turns of the protein helix at a radius of 40 angstroms. And that was different from incorrect model that Jim Watson and I had made, misinterpreting some of my data. Now it's going there. So at the same meeting, Jim Watson and Francis Crick described their ideas about the symmetry, possible symmetry of the isometric virus particles, that they predicted that these spherical virus should have cubic symmetry, tetrahedral, octahedral, or icosahedral, and was the reason I had come to Great Britain in 1955, and had, by a fortunate accident, found, recognized five-fold symmetry in the virus particle. At least with bushy stump virus, it was icosahedral. So here we are. This was just a few weeks later, April, in Madrid, at a crystallography meeting. Ann Cullis, who was working with John Kendrick, Francis Crick, Aaron Klug, Rosalind Franklin, both Crick and John Kendrick. So I must say, I was a bit impressed about the virus crystallography because John Kendrick had a crew working on phasing myoglobin, and I could see no way that I was ever going to have anything to do with finding atoms in a virus structure. But 2 years later, 1968, 1956, Kendrew produced a 6 angstrom resolution map of myoglobin, and I think many of the scientists who looked at it thought it looked rather revolting, that it was Frankenbrew's monster. But 2 years later, they weren't laughing that John Kendrick had determined the atomic structure of myoglobin, the first protein whose structure determined the atomic resolution, and the realization of the anticipation that Bernal had in 1934. So 1960, Ken Holmes came to work with me at Children's Cancer Research Foundation here in Boston, and Aaron Klug was visiting at the same time, and Ken was supposed to be working with me on the structure of tuberculosis virus, but my colleague Carolyn Cohn, she was, one of her ambitions was to try to get the photograph 51 that Francis Crick calculated from the coil. And she had found a molluscan muscle specimen that was highly oriented, and then she conned Ken Holmes into taking the diffraction pattern with focusing monochromator that he was setting up for the TMB work, and sure enough, there was split equatorial reflections predicted by Francis Crick in 1953, and all the other details of the call structure. And actually, for our work on TMV, this turned out to be a fortunate distraction because we observed forbidden reflection in it was Dolomensi strain of TMV, and Carolyn was able to tell us how to make sense of it in terms of Francis Crick's call theory, and it involved periodic perturbation, so the protein molecules were 98 different conformations within the structure. This was sort of the beginning of the idea of quasi-equivalence, which led to the theory that I formulated in 1962 with Aaron Klug. But 1962, sort of more notable things were happening that Jim Watson, Francis Crick, and Morris Wilkins won the Nobel Prize for discovering structure of DNA, and Max Roots and John Kendrick got the prize for their work on the structure of proteins, and they had, with the papers I'd shown from the MRC group, that the laboratory was called the Medical Research Council Unit for the Study of the Molecular Structure of Biological Systems. Well, when they finally got their new building, this was called Laboratory of Molecular Biology, and with the stars there, John Kendrick, Francis Crick, Hugh Huxley, Max Roots, Fred Sanger, and Sidney Brenner. This was now the world center for molecular biology. But 1966, Linus Pauling had his 65th birthday. So his students, colleagues, and friends got together, make a festschrift for him, structural chemistry and molecular biology. So this was the, let's say, this was the Pasadena School of molecular biology based on structural chemistry. Now, I needed to get a copy of this book 3 years ago, and I found I could get actually an unused remainder through Amazon.com. It was 85 cents, which I think is a mark of, let's say, its historic significance. But 1966, the guy next door to Linus Pauling at Caltech, Max Delbruck, he was 60 years old, and his students, colleagues, and friends got together to do a festschrift for him. And as you can see, this was called Phage and the Origins of Molecular Biology. And this is the centennial edition. It's been reprinted by Cold Spring Harbor Press on the 100th anniversary of Max Delbruck's birth. And you can get a copy, a really fresh copy of this online for $30. So John Kendrew wrote a very influential review of this book in 1967, and he was certainly struck by the fact that the Delbruck book was all about information in biology. And they said in the British school, which stemmed from the early studies of Asprey and Bernal and their pupils, the emphasis had been on structure rather than information, on knowledge of structure. That's the only road to understanding biological function. But the laboratory that Carolyn Cohn and I had at Children's Cancer Research Foundation, the Chewy Fund, that we thought we were following in the footsteps of Asprey and Bernal, and so we thought we were doing molecular biology, but I think it was pretty obvious then that the name was being commandeered by all the scientists who were working on the informational aspects of biology. So my colleague Carolyn Cohn decided we needed to change our name. So we were then a laboratory of structural molecular biology. But a few years later, actually 1970, the Rosalind Center at Brandeis was about to be built, and we were told that we were going to be offered jobs there. But well, first we had to design a laboratory because they were about to build a building. And I must say, I did not like the idea of starting a new laboratory and having it called Laboratory of Structural and Molecular Biology, because it sounded like we would be some sort of appendage to the molecular biologists, and also, with what Asprey defined as molecular biology, he said it's concerned particularly with the forms of biological molecules and with the evolution, exploitation, and ramification of those forms in the ascent to higher and higher levels of organization. But the higher levels of organization, I'm sure what he was thinking of was Darcy Thompson. Darcy Thompson's growth and form had profound influence on the British School of Molecular Biology. The first edition was 1917, the second edition was 1941, and it's full of wonderful information about biological structure. It doesn't have anything to do with atoms or molecules. So I figured that what we were doing, that really the future was the higher levels of organization, and we should not exclude that from names. So the name we chose was structural biology for our lab when we moved to the Rosalind Center. So here is Carolyn Cohn, David DeRose, Susan Lowy, and myself. Now, this is actually the end of my story about the origins of molecular biology, but I would like to have a little code about history. So, Bragg had written that science is unlike the arts, where the value of original thought is often enhanced by time. Science is like a coral reef, alive only on the growing surface. But I think, and many scientists do tend to think like this. What's interesting is just what's in the latest issue of Nature or Science, and stuff that's gone before. But on the 100th anniversary of Bragg's invention of Xray crystallography, who could consider that the value of his original thought has not been enhanced by time. Now, another quote about history. David Ben-Gurion's first Prime Minister of Israel, he said, anyone who believes you can't change history has never tried to write his memoirs. And I think that, let's say the examples with the alpha helix and the DNA structure certainly tells us. So this was November 1953 in Tel Aviv with David Ben-Gurion and Linus Pauling. So now this is the end of my story, or the end of the story about the beginning of structural biology. And I realized that that the proper thing at the end of the talk is to have an acknowledgement slide. And I forgot to do it. So I have to thank George Phillips for helping with an earlier version of this story. And there was my student Eric Fontano, and most recently Esther Bullock. So this is the end. Thank you.